Thank you. Okay, I'm very grateful to the organizers for this opportunity to give a talk. And this is a work which we are doing with various groups for the last maybe 2 years. So roughly here there are all publications or papers about to be published, presented, and my co-authors. So hope the title itself can serve as an introduction. I will quickly come to the model which I will be studying. So it's gamma twisted super Yang-Mills theory in a specific double scaling limit. So we start from the standard n equals 4 super Yang-Mills. Here it's without any twisting. You have here 3 complex scalars, 4 fermions, etc. Now let's twist the theory. Twisting means that you replace a product of matrix product of fields. Of course, they are fields in a joint. So if A and B are products of two neighboring fields, then the star product will enter with a specific factor Q AB, which is an exponent of antisymmetric combination of bilocal combination of 2 charges J of A and B field respectively, and so if you exchange B with A, it becomes 1 over Q. So the commutator becomes Q commutator, etc. And of course this deformation depends on 3 parameters, 3 twists, gamma 1, gamma 2, gamma 3, which correspond to 3 Cartan charges. You choose 3 Cartan charges, J1, J2, J3. Okay, this is quite a standard deformation proposed by various people on the CFT side or on the AdS side. And what comes out is the following. The interaction terms, of course the Gaussian terms, the Gaussian part doesn't change, but interaction terms change. There are various factors like e to the plus minus I gamma appearing here and there. So these gamma plus minus are defined also through gamma 1, gamma 2, gamma 3. So you get various factors which of course destroy almost a good part of the R symmetry, original R symmetry, leaving only 3 subgroups U1 corresponding to each gamma 1, gamma 2, gamma 3. So, and our idea is the following. Let's go to a specific double scaling limit of a very strong imaginary twist. So gamma goes to I infinity in order for this factor to go to infinity, and also weak coupling, G goes to 0. In such a way that 3 constants corresponding to 3 gammas, this product G times the factor, remain fixed. And it's immediately clear that all the gauge interactions go away because they are not twisted. It's the twist on the R symmetry side. Then many terms, of course, disappear because they have negative powers of this twist, and only these terms survive. So the interaction doesn't contain now covariant derivatives, usual derivatives only, and you have 3 phi-4 scalar interactions of complex scalars, and you have various Yukawa couplings with very specific couplings. You have three arbitrary couplings now. The supersymmetry is also destroyed unless you take all three couplings equal, then n equals 1 is still preserved. And you can notice that, of course, since gamma is taken imaginary, the theory is not unitary. And you can easily notice that if you take some term, its Hermitian conjugate is absent here. So all these terms have left their Hermitian conjugates. It's a very specific theory, but presumably integrable, because after all we start off from an integrable deformation of n equals 4 super young Mills. So the original superconformal symmetry is broken up to subgroup which is a conformal group. At least naively it's not broken. We conserve all the conformal properties, but of course we have to watch the anomalies, conformal anomalies, and also the U1 cube is residual R symmetry. So this is the most general model. Now there are actually some other deformations of a similar type, but this is about the most general model we can consider. But now we will quickly reduce it to the most emblematic case when we take two couplings to 0, say xi1 and xi2. Then all three terms here disappear simply because they have everywhere these couplings, and only one 4-scalar interaction is left. So we are left with a theory which we call bi-scalar chiral conformal field theory. It's presented here. You have 2 out of 3 complex scalars left, and also their chiral interaction. You have this term, and the Hermitian conjugate is absent. So it looks very simple, but first, it seems it could be considered as a conformal theory on the one hand, and on the other hand, there should be some simple integrability properties here, and maybe we can learn something about integrability of the full n equals 4 super young Mills, which is still a mysterious issue. So let's look at the perturbation theory at Feynman rules. We have propagators of phi1 and phi2 fields drawn in double lines here in order to go to 't Hooft limit. So phi1 field has this solid line propagator, and phi2 dotted line propagator with standard massless form in 4 dimensions. Now the only vertex looks as follows, and we have to watch the directions of propagators. Of course, we have to draw here the arrows, these red arrows, which go from phi to phi dagger fields, so that there is a certain chirality in the sense of Feynman graph. So there is a 2-dimensional structure in the form of Feynman graph. So for example, here, if you go clockwise, the phi1 type propagator with the arrow out is followed by phi2 type propagator, and so it's a clockwise orientation. Whereas the missing anti-chiral vertex with the opposite direction of one of the arrows, which would complete the theory to the Hermitian one, is absent. So we sacrifice unitarity, but of course, for example, if we added this vertex, there is no way to have a conformal theory out of it. But here we somehow preserve conformal properties. And moreover, there is a very limited number of planar graphs in this theory. You will see that roughly it's at most 1 graph at each loop order. It's very rough characterization, but it's almost true. You'll see the examples. But these graphs may look conformal. They may define conformal theory. let's demonstrate that there is no mass and or vertex renormalization in this theory. For example, the lowest vertex renormalization diagram looks as follows, and you see that you necessarily have one clockwise oriented vertex here and another anti-clockwise. Otherwise it's non-planar, so we exclude it. And one can see that higher graphs renormalizing this vertex can be excluded, are excluded by this rule. Same about mass renormalization. It should consist of one clockwise, one chiral, one anti-chiral vertex on the planar graph, again excluded. But unfortunately, or maybe fortunately, there are double square coupling, double trace couplings which run even in the planar limit. So there is a conformal anomaly, but it's sort of like a tachyon in string theory. You know that you have tachyons in, say, in 26-dimensional string theory, but if you measure the Shapiro-Virasoro amplitudes out of tachyon pole, it looks like a normal theory, and the problems start when you start calculating the usually start calculating the string loops. Same story here. 1/n squared terms or very specific operators will have conformal anomalies. But on the other hand, as we saw, the coupling psi square is not renormalized. That's why many correlators, most of the correlators of the theory, if they don't have length 2, for example, will have conformal form in 4 dimensions. So we can really study this theory as a conformal theory and calculate various physical quantities as in the conformal theory. Okay, so this is sort of the introduction to this model, and now let's try to study particular physical quantities. Let's start from amplitudes in this bi-scalar model. So we start off from formulating a single trace correlator, something similar to Wilson loop. Namely, we just multiply fields in various points, x1, 4-dimensional point, 4D points, x1, x2, etc., x to m, and each chi field is one of 4 scalars or their conjugates, of 2 scalars or their conjugates. And now if we look at the graphs, the only graphs in planar limit, of course, we look at the planar limit only, the only graph the only type of graphs we can draw look as follows. So if you order the fields phi around the boundary, then you see that there is either no way to connect phi's by these lines. The lines shouldn't be interrupted because our vertex has this structure like phi1 dagger, phi2 dagger, phi1, phi2. And we know that yellow lines corresponding to phi1 shouldn't cross. There is no such interaction. Black lines either, and also the chirality should be respected. The arrows should be respected. Then there is either one way to connect them or no way at all. For example, if you interchange these 2 fields, phi1 daggers, then there is no diagram, no such diagram. So, and each crossing is of course a 4D integration. It's a what happens? It's a multi-loop diagram, and the number of loops depends on the ordering of fields. So it's curious. You have a conformal amplitude, and you have to compute one graph, although this graph might be very complicated. Now, if we look at the structure, typical structure of such graphs with many fields, for example, at the boundary, they look like Fishnet graphs. Something like a disk cut out of the square lattice. So take a sheet of square squared paper and just cut along a sequence of bonds, cut out a disk, which is shown here by solid lines. So this is such a correlator graph. All these internal blobs are integrated out. All the boundary points are at fixed positions in X space. And it's essentially about everything you can do with these amplitudes. All the graphs look this way. And the longer is the boundary, the bigger can be the graph, but inside you will see more and more of this fishnet structure. Now, if we want, instead of these correlators, the amplitudes, we know what to do. We have to, in particular, massless amplitudes, like the ones which I usually studied in N=4 super young mills. So we have to amputate the exterior. No, first of all, we have to go to the dual picture, to the dual momenta. So axis, the original axis, play the role of region momenta. Then each x is the difference of two neighboring p's. And then we have to also put these p's, or actually the differences of neighboring axes, to the light cone. And also with this, since the original correlator graph is this double cross, and we want to complete it by these crossing lines, we have to add additional propagators here. So this x1 is sort of a fictitious point from the point of view of this, in order and the particles, scalar particles, which have these trajectories, let's say so. So it's a regular procedure to get a correlator out of this, to get a massless amplitude out of this correlator graph. Okay, and it appears that these graphs are manifestly finite and also dually conformally invariant. Finiteness is a subtle. All the specialists, I wouldn't say that I know the proof for any such type of graphs, but the specialists say it's obvious. We checked it for some particular configurations. They are finite indeed. And it's a good news for various integrability schemes, because usually the Yangian symmetry, which people were searching for in full N=4 young mills, are so the Yangian symmetry is severely damaged, I would say, or at least hidden due to the various singularities, infrared singularities. And here it seems we don't have the problem of singularities, and we have a nice integrable structure and Yangian symmetry, which I want to demonstrate. For that, I from defining the so-called Lux operator, which will help us to formulate this Yangian invariance. Since we know that the symmetry of our model is essentially conformal symmetry with the group SU2, 2, it's natural to construct a Lux operator, sometimes called R matrix, as a linear as a linear in U, in spectral parameter U. So you have the first term U times delta alpha beta, a 4 by 4 matrix. All this is in indexes alpha and beta, it's 4x4 matrix according to the rank SU2, 2,2. And then you have the standard combination of generators in auxiliary space and generators in quantum space, in physical space. So in auxiliary space, we take fundamental of SU4, and in quantum space, the principal series representation of SU2, 2 standard set of conformal generators in 4 dimensions. And as it was noticed in the paper of Checherin, Isaev, and Derkachov, these Lux operators can be nicely factorized into 3 simple factors. Here the definitions are as follows. U plus and U minus are combinations of U, linear combinations of U and conformal dimension, the dimension of representation, delta. We have the representation, conformal representation 0, delta 0, with the labels 0, delta 0. So in some sense you have 2 spectral parameters, U plus and U minus, although they are simply combinations with delta, since sometimes it's convenient to keep delta arbitrary, although our spins have dimension 1, they are scalars. And then these X and P are contractions with Pauli matrices. So each element here is a block 2 by 2, so it's 4 by 4 matrix. And we will denote it by by such a cross where the blue line corresponds to compact space, SU4, to the matrix space, let's call it, and the black line to the quantum space defined by differential operators. Yes, like P is the derivative, for example. Let's remember it. Okay, so this is the main element. Of course, this L satisfies the Young-Baxter equations, and it defines a nice conformal spin chain on a group SU2, 2. In principle, we can study the corresponding spin chain, non-compact spin chain, which we'll do in a moment. And let's list some interesting properties useful for formulation of Yangian symmetry. So there is the inversion property. You can invert L by shifting these 2 parameters, U plus, U minus, and taking transpose in quantum space. Then if you act on unity, an important relation for us, if you simply act on 1, then, for example, P disappears since it's a derivative, and you can easily see that the result is simply U plus 2 and times diagonal matrix. It's U. Then you have very important, maybe the most important property, intertwining property. If you have, so it's better to demonstrate it on a picture. So you have the product L1, L2, 2 such factors. It's important that here U, the left argument, and here the right are shifted by 1. And here the propagator 1 over x12 square is on the left. So these operators, so probably this configuration corresponds to that picture. Both L1 and L2, first they are multiplied in the, they are acting on various ends. Say L1 acts on x1 variable of this 1 over x12 square, and L2 on x2, and then and then they are also acting on each other. So this is suggested. You also contract the matrix index in this way. This intertwining property says that you can push x, this propagator 1 over x12 square, through L's, so that it appears to be on the right and nothing acts on it, and you have simply the product these two L's. So this property we should remember. We also have similar property for the so-called cut of this propagator in Minkowski space, the delta function of x12 square. Everything is similar. There is a cyclicity. You can put here L1, the last L, to the left. When G is our graph, so we are acting by L on a graph, or on a spin chain sites, let's say so. And there is the cyclicity property that you can put L1, Ln you can put to the right by shifting according to the argument. Okay, now we shall use these properties and formulate Yangian symmetry first for simple graph which we call cross graph, a famous graph which was studied in many occasions as quantum field theory. Simply one integral with four massless propagators and fixed points on the boundary. And the answer is known. It's given in terms of Lie2 functions, the polylog. Everything is expressed through cross ratios. And then we call our method lasso method because we sort of throw on a Yangian product, a monodromy as lasso around our graph. So here you have the Lux matrix acting on this leg, then they are connected in matrix space. Here it acts on this leg, etc., and you finish here. It's a monodromy. You don't take the trace with respect to matrix indices. And now we want to show that, in fact, this monodromy acts in a diagonal way on our graph, Feynman graph. What we do, we insert using, probably I should remind you, this property, action on 1. We insert simply constant up to some factor u+2. Insert a constant inside the graph, but integrating by parts, which means that you exchange t to you act by the derivative inside the integral. Instead of acting to the right, you act to the left. You insert this monodromy, acting on all four legs at the same time. So first you insert it as a constant, then integrating by parts inside the integral, it appears acting on all four propagators on the side of this coordinate, which is integrated. Okay, then you get this contour. And then you use the property, for example, you want to push this part of the contour through and get this one. You use this other property, intertwining property, this one. Of course, by respecting the factors. We denoted here the factors, various factors, u+2, for example. Where is the notation? Was probably I forgot to introduce it. So this is, for example, u+2 in square brackets, the extra factor which appears here. And in the two indices in two numbers in the square brackets, it's simply we characterize by it the spectral parameters of corresponding Lux matrix. Okay, then we essentially push this part of the contour through. We get this. We push this one through. We get this, that, and finally we free completely from this lasso, from monodromy, our integral. Simply multiplying it by specific factor. Here it's u+4, u+5, for example. So this is more or less the Yangian symmetry, explanation for Yangian symmetry of this cross graph. Yeah, that's the expression. Yes.
Suppose you don't know the right-hand side of the equation. Can you reproduce it from
We got actually. We are working on it. We got some expression, differential equation on z and z bar variables. It looks, for the moment, it looks different for us than the equations which people usually write for this integral. Like you act by Laplacian on one leg, and you get sort of Laplace equation in z bar variables, or Poisson equation. It satisfies the expression satisfies our equations. What can I say? But I wouldn't say we guessed it. We knew the answer. But for example, for double cross, this is double cross. We can obtain differential equations also in this way. It's the same story. We insert Lux acting on unity with such arguments that you can insert it as a constant, then integrate by parts, connect this way, and then you push through this part, little by little you free from this lasso the graph. Here we have an equation, and I'm not sure people have good equations for this double cross, but everybody promises to calculate it in elliptic functions, sort of, but nobody saw yet the answer. So we have some nice differential equation here, and our equations are always second order. What is interesting in cross ratio variables. So here it's in algebraic form the action of this monodromy on. I wanted to say double cross integral here. It should be double cross, and this factor is simply u plus 3 square, etc. And now, what is the general scheme? Yangian symmetry of a general bi-scalar Fishnet graph. It's something like that. So you have again this correlator graph cut out of the a sheet of square paper, and you form the monodromy with very specific spectral parameters here. Like on this boundary, it's everywhere 1, 2. U plus and u minus are equal 1, 2. And when you turn by minus pi over 2 degrees, minus pi over 2 angle, then you add 1 unit to it. If you turn back, you subtract again 1 unit, etc. It's a very simple rule. And the answer, the general relation of Yangian symmetry is also very simple. This product acts on the graph G as if it acts on a wave function of spin chain. So, but only the wave function, the coordinates of the wave function are external coordinates of this graph, and the action is diagonal. It's just a factor times this graph. Here is the definition of the shifts. Okay, and if we expand this monodromy in terms the left and right hand side in powers of u, we can restore already, we can write the differential relations. Namely, we can get Yangian generators of level 1 in a very explicit form. Okay, here I show how to pass this lasso little by little through the graph by these elementary operations which I showed on the example of cross and double cross. Let's go further, and then we have this Yangian algebra. You have level 0 operators and level 1 generators of this algebra. Then there are standard relations which associativity, the level 1 serendipity, definition of coproduct, because we act on various sites, on many sides of our spin chain, and then we can construct the generators of level 1 in a standard way. It's known that you can add linear combination of these of level 0 generators, and the whole interest is in computing this VK, the coefficients, which are arbitrary for this algebra but specific for each graph. And here is the particular formula for these generators in terms of matrix for generators rho CD of conformal algebra instead of J. I mean, you have very specific form of these VKs through these factors U plus delta U. Then we have particular differential equations for single cross, for example, in terms of these original generators, specific numbers here in front of P. P is Poincare generator, and L it's rotation, Lorentz rotation, and D G is the dilatation operator. Similar expression for double cross. So here are this is a new equation which might help to compute this integral, for example. Okay, now I have 5 minutes. I wanted to also to present for you to you some results of computation of correlation functions and anomalous dimensions of operators of this form, say single trace operators, which consist of phi 1, phi 2, two scalars, which form sort of a spin chain, and correlators render to you anomalous dimensions, and it's easy to see that if we, for example, study the BMN vacuum operator phi 1 to the L trace, so the only possible correlator, the graph for this correlator is this kind of a globe type. You have phi 1 lines going from 0 to x, and then the only possibility to turn on interactions is to have phi 2 lines, dotted lines, dotted red lines, and at each crossing you have interaction vertex. So it's a multi-loop graph, which in principle we should be able to compute using integrability. Ultraviolet reduction of this graph consists of cutting out this cap in the UV, because we know that in UV that everything is defined by the vicinity of one of the poles, and you get so-called wheeled graphs. If you insert magnons phi 2, for example, here we inserted 2 magnons, so you will have this kind of spiral graphs, and if you cut a cap, you will get spider web graphs, also integrable graphs. They have typical fishnet structure, and Zamolodchikov once showed that at least in the bulk, the fishnet graphs are integrable. So this bi-scalar model is a nice realization of Zamolodchikov's fishnet graphs. We also are actually computing the 4-point functions now, and this is the only graph which contributes to 4-point function of these operators, and you can probably have here a possibility to compute exactly the 4-point function of this conformal theory, and to extract all this nice OPE structure constant, etc. in potentially in all orders. Here it's possible. I don't think it's possible in the full n equals 4 Young-Mills, but in this theory it might be possible, and we might learn something interesting about conformal, 4-dimensional conformal world. For example, for one wrapping, we computed using Volodya Smirnov ingenious methods. We computed for this object in terms of polylogs, and already there are very interesting structure constants coming out from it. Okay, and the last thing, minutes, I wanted to show, maybe I will only show you the results of our calculations, very recent calculations of the graphs for of wheel graphs with 3 spokes and any number of frames, let's say. So this graph, and we reduced with Nikolai Gromov, Grigory Korchemsky, Stefano Negro, Gregory Sizov. We used the problem using integrability, combining quantum spectral curve methods and also just conformal spin chain. We discovered for these graphs at any order that we can write the Baxter equation of this form, where delta is the anomalous dimension and m, here the coefficient m, is directly expressed through coupling psi cube of this bi-scalar model. Then we derived from quantum spectral curve the integrability condition in terms of 2 solutions. Let's call them Q2 and Q4, 2 solutions of this equation, having specific asymptotics.
Would be that function with the 2 poles, you square you cubed, or you the one I guess multiplying the first q, no? This is the t.
I didn't understand the
No,
question.
in the tq function, in the Baxter equation.
Yes.
You assume the t function to be, what is a usable definition of the t function?
T
Usually
here.
T is analytic. Instead it has
That you call
0.
what is in the brackets you call t function.
Yes.
Okay,
yes.
that's the whole point. You have to fix it. You fix it actually from asymptotics already. You can fix it from asymptotics. It's more complicated to fix m in terms of coupling. You have to go through an area of spectral quantum curve, which might be also an overkilling because you simply deal with this nice spin chain, conformal spin chain. But it is now at this stage. So I cannot. Almost everything is fixed apart from this, and that is fixed from asymptotics and algebra.
Is the t is not analytic in 0, no?
It's actually you should no. You simply have to redefine this q by a power. It will be of course just a potential polynomial t.
Extract some new power, yeah.
Mm-hmm. It's just a redefinition, and at the end you can study these equations analytically and numerically. And for example, analytically with huge precision, which Gromov and his collaborators worked out specific methods for this kind of calculations. You have anomalous dimension which is real up to some transition point, then it becomes imaginary, which is normal for non-unitary theory when it hits the actually the unitarity bound at specific point. And then you can generate many orders of perturbation theory exactly with all details. So these 2 were known from direct graph calculations. They are reproduced here, but then you can have how many 9 loops, then I think it's 12 loops, etc., everything in terms of zeta numbers, etc. Okay, I think I have to stop here. I will pass to conclusions, and also if generalized to any L, for example, Baxter equation at any length, any number of spokes is known, and I wanted to talk about specific stringy behavior of this object. It looks like a strange 4-dimensional string theory because we found also at large size of these operators, we found sort of a classical limit with normal finite gap type conditions, and now I simply pass to the conclusions here. So we presented here the double scaling limit of twisted n equals 4 super Yang-Mills theory, which looks explicitly integrable in planar limit at each loop order. Physical quantities are dominated by integrable Fishnet type graphs, and they can be potentially computed. Many of them can be computed by integrable conformal spin chain methods. Similar story exists also for ABJM model in 3D. Also a nice four-scalar 5 to the 6 interaction. Then also six-dimensional case could be considered, six-dimensional theory, although we don't know which super Yang-Mills theory it corresponds to. And corresponding amplitudes based on these Fishnet graphs, triangular or hexagonal, also can be studied. There can be also graphs composed from Yukawa vertices in 4 dimensions of this kind of hexagonal kind. There are many directions here, and I think potentially it's also very useful tool to compute interesting Feynman graphs, multi-loop Feynman graphs. And the last thing which I will say is that theory is also a very nice example of 4-dimensional logarithmic conformal field theory. Because of non-unitarity, you will for sure have here logarithmic multiplets, which represent sort of what is called Jordan cells in mixing matrix, and in principle I have examples here of this behavior. That's probably the end of the story. Thank you.
Hexagon graphs are also integrable in this Zamolodchikov sense?
Yes. Zamolodchikov considered precisely 3 types of graphs, which can be obtained in various limits from Baxter lattice or even Kagome lattice. In various versions you can get square lattice or triangular or hexagonal, and you can cut amplitudes out of, for example, hexagonal lattice of triangular. There is a similar story behind it in terms of amplitudes.
But there is no underlying super Yang-Mills theory that would be integrable.
The gauge field disappears from these theories, so maybe one can try to restore them by twisting the conformal part, the Lorentz group, the conformal group, but here there is no gauge field, so you can have fermions and scalars. Various mixture of fermions of scalars is also possible. For example, this one, you can have these vertices as Yukawa vertices. You have scalar, fermion in each vertex, and it will be in 4 dimensions also, an integrable graph.